Okay, as is our custom, we will often recapitulate what we've talked about previously, and so today is no different from that. Um, and so we've made the point that in these systems, when you spill something, in the first little while being a few weeks to months to less than a year, probably, almost certainly less than a year, that you get an architecture that's set up in the subsurface. And we'd like to know something about that architecture because if you want to remediate it, then the format of this, as to whether it is all smear or whether it has lenses that are pools at different levels and why they might be at different levels, is probably some interesting information that you'd like to have to kind of direct your efforts. We'd like to also know what the distribution would be within these saturations in these smeared chimneys, which would be at relatively low saturations of the non-aqueous phase liquid. And we saw why that might be last time, and we'll reiterate today. And we'd also like to know whether it would accumulate in pools like this and why it might. And we now know something about why it might do that. We looked at a couple of different approaches to do that, and so number one was that we said we could take capillary tubes, and those capillary tubes would say something about the the height rise of a meniscus above a point, and we could convert that height rise into an equivalent capillary pressure, not the same units. And depending on the geometry that we looked at, whether it was a tube, which might be part of the pore space within a porous medium, or a fracture that might be one of the easy conduits for this to go down, then the capillary pressures differential within, can you see this, by the way? Would be something like 4 times the interfacial tension divided by the diameter of this tube. And in the case of it's a fracture, which also might be a fast conduit, which has some aperture B, that the capillary pressure might be equal to 2 times the interfacial tension divided by the aperture. So when this aperture or this diameter gets to be small, you have to have a big pressure to be able to push stuff along it. And this capillary pressure is just defined as the pressure in the non-wetting fluid versus the wetting fluid. Typically, the wetting fluid is water, and the non-wetting fluid is NAPL. But sometimes, for instance, in the unsaturated zone, the wetting fluid may be water, and the non-wetting fluid might be air, which is present. And so these are 2 expressions that relate to saying something about the pressure you'd have to apply to force something into the system. So that's the first way that we looked at it. The second way we looked at it was that instead of taking this system and thinking about a single capillary that maybe would represent this, you could imagine that this might be a single capillary tube as a pathway between these grains. Then the other way to look at it was that we'd like to be able to take a box, and we'd put this box around it, and we look at how this box could be invaded by the same fluid, not just to determine this one piece of information, which is, if I make the noise right, what it takes to go into it, right? When it first invades, gets over the threshold, and therefore can get into this porous medium, but to progressively say how much of the available pore volume it might take to be able to fill it up progressively. And so our approach to look at that was to talk about this experiment that we could do, where we could take a core and where I did it bass backwards last time, but we'll do it properly this time, that it has a saturation of water. The opposite is true on the top axis, saturation of the non-wetting. And we could have, for instance, capillary pressure, the difference in these two pressures on the vertical axis, from 0 to a big number. Or it could be defined in terms of this non-dimensional term, the J function, which is a normalized capillary pressure. So it's a capillary pressure which we just do something with. And what we do with it is we divide that capillary pressure that we measure by the interfacial tension, and we multiply it by the ratio of the permeability of the medium and the interfacial, so permeability medium and the porosity, square root. And we do an experiment to basically take this core and start invading it with water. So we start with water on the outside, so we start invading it with oil. We start with 100% water saturated, and we raise the pressure in the oil that surrounds it, nothing happens. We raise it a bit more, nothing still happens. We raise it a bit more, all of a sudden it's right at the threshold to the gates of hell. As they'd say, everyone watch Christmas Vacation? Do you guys have Kleeman classes? Isn't he a movie aficionado? Don't you watch with your families? Jeez, you're at the ages of my kids, and so don't you watch with your? Don't your parents make you watch Christmas Vacation?
We don't salt lampoon.
Yeah.
Yeah.
We're standing at the threshold to the gates of hell, says Clark Griswold as Cousin Eddie is emptying the sewage out of his RV into the sewer, as I recall. Anyway, so I don't know why that came to my mind. So anyway, so capillary pressure versus saturation curves. It kicks off here. It would be some what we call as PC0 or a bubbling pressure, PB. We use those terms interchangeably. It's when you force the first bubble of oil into the system, and all of a sudden you saturate it at 0% saturation, 0.00001% saturation of oil, and it's got the first slither of stuff into it. Keep on increasing the pressure after that. Let me do this. You take it up a notch. Next point, up a notch. You'll get an assignment, by the way, to do exactly this. So you increase the pressure. It slowly lets the fluid go into it, comes to some equilibrium, and then it defines this capillary pressure versus saturation curve. We know that usefully, and actually which is defined by this, usefully, the number where this occurs is always roughly the same number. And that basically represents the first largest capillary that we have in the system that gets invaded by this material. And it's always 0.3 for this value. And so this intrinsically, and it's a useful curve. Maybe I found out how to use different colors on this, so I started using them. This is what we called, this is supposed to be a single very thick line, but this is what we call the drying curve. Goes up to infinity, then when it comes down, it's an imbibition curve which stops off at a different place. And so we know, we said last time that there are a couple of parameters that we define on this curve. And this is the irreducible saturation of water, or wetting saturation, and the irreducible saturation of the non-wetting component. And they kind of define no-go areas that we can't get back into. And so the point of recapping this is that this is the physics that's going on. We're trying to push things in little capillaries. If they're too small, it won't go in, and therefore we can define a threshold pressure that we have to apply. That is basically this point here. So this gives us one piece of information, but really only this point. And so the reason that these curves are better are that they give us much more information because they say how the saturation would change as a function of the capillary pressure which is applied. And so intrinsically, and we alluded to this last time, if we know what this capillary pressure might be in our system, then we know what the saturation could be, and depending on which path of this figure we are. And so hopefully we can figure out which path we're on. If we're not, then perhaps we can just take one of these curves and then just use that. And that's where we were last time. What we did do, I guess, also was we took a fancy way of taking this curve and to modify it slightly. And you'll remember that if we cut this curve off at this particular point here, basically made this 0 and wrote this as an effective saturation to 100% here, then we could draw, and someone pointed out, why did we switch this 90 degrees? But we did. We could draw a curve that had something about effective saturation of no. It wasn't, was it? It was capillary pressure, because it would be the same as this, right? It was capillary pressure divided through by unit weight of water, and it was effective saturation, and there were the logs of each of these. And if we did that, then we had a kickoff point that was here, and then a graph that had some gradient to it. And I think it was an expression that was something like SC is equal to capillary pressure divided by unit weight, but also divided by the bubbling pressure divided by unit weight. So the unit weight cancels out to the minus lambda. And I guess by definition, this log is 1, which I guess is 0 if it's the log of 0. So this is saturation equal 1. Because you're here, right, at this point. Start off 100% water saturated, you increase the pressure away from it, you reduce your saturation. And so at this point here, this is 100% saturated. And that was just a different representation of what we were trying to do. So that's kind of where we were last time. So bottom line is, take-home message, we can do this. This gives us one data point, which is here. If we look at these capillary pressure curves, by getting these curves, it gives us much more information about how much stuff we have in the subsurface, and therefore we might know how much we want to take out of the system to be able to do that. So that's kind of where we left off last time. So hopefully everyone's okay with that. Yeah, I guess I'll go back to the notes. And we'll continue. So 2-2, that was last time, so you recognize this. Yeah. So here's the reason that we're interested in it. And we probably, this is a bit more than we need right now. We'll come back to this, but let's absorb this first. So you see a couple of diagrams here that hopefully should look at least a bit familiar. And that's this diagram here, which should look absolutely familiar because it has exactly the same axes as before, and it's in its inverted form here, right? Just flipped it. And so these have been drawn specifically in this geometry to represent two cases. On the left side, we're talking about the vadose zone. By definition, the vadose zone is everything above the water table. And so if you think about the water table, this is a little vertical cross-section. This is the water table. Everything is saturated below this. This is the so-called tension-saturated zone, the capillary fringe, where there's enough surface tension to physically suck up this water so that even as you get to this point here, it's 100% filled with water and 0% filled with the other component which could be present in the vadose zone, which is air. And then as you go above this, it's progressively less and less filled with water and more filled with air, which is exactly what this is showing. And so we've talked about it in terms of oil invading water, but the non-wetting fluid could also be air. You could be pushing a bubble of air into the system, and in which this case it represents the vadose zone. If we flip it, we're going to come back to this. If we flip it, so this is our capillary pressure versus saturation curve, then this now represents the water table and the free surface, the ground surface. So this is the surface of the ground. Water table is up to the surface of the ground, and now you have your happy-go-lucky 55-gallon drum. I love this. I'm an artiste that's gone into here. And now the green stuff is our denser than water NAPL, and the blue stuff is the water that surrounds it. And so as we look within the swimming pool, actually why don't we deal with it now? We know that the pressures as you go down in the subsurface, if you're in a swimming pool filled with water, the pressure would change as 1 over the unit weight of water, which is this. If we go into this, if you fill the swimming pool up with a dense fluid which say has a specific gravity of 1.6, which might be what these NAPLs are, then the pressure in the swimming pool on its own would go down at that rate. If you look at having both of these fluids in the same system, and so long as they're connected, so long as the green fluid is connected all the way down to this point here, as you go down to it, the pressure that you'd feel, if you could keep it in a swimming pool, would be the pressure in that liquid. The fact that it's in a porous media doesn't make any difference. And so at this particular point here, the pressure that you'd have would be this pressure here. If you went down a different path in the porous medium, in the water, to get to the same point, right next to this, and you wanted to know what the pressure was, it would be this value. They're different values. The difference between these, by our own definition, is capillary pressure. And so this bridge between here is actually the capillary pressure. Capillary pressure difference, I guess we'd call it. It's capillary pressure is the difference between the pressures of the two fluids. So at this point here, we're at zero depth, and so the curves are coincident. As we get progressively down, one is increasing faster than the other, so this just grows linearly. So you could think of this depth, if you like, as the pressure is equal to depth times some constant. And that constant is given by this difference here. You could calculate it if you want. I suppose we could do it if we wanted to, right? I guess it would be, physically, what would it be? Any thoughts? I think. I'm pretty sure. That's it. Of course, that's exactly what it is. So, and graphically, it's 0 here because z is 0. It's a bigger number here because z is no longer 0. Double the depth, it would just double. And so what you could do is, instead of defining this length as z, you could also label this axis as PC, P sub c, because they're directly linked to each other. They're linearly dependent. And so what you could do is draw this axis here, which is PC. And so what this is saying is that as you start off with a capillary pressure of 0, then you have 100% water saturation. Ignore the fact that you have this slither going down here. As you go down here, you still have 100% water saturation. But as you get to this point here, it doesn't correspond directly across here, but this point here, didn't mean to make that jump. At this particular capillary pressure, then you have the saturation of water is, I guess, I specifically didn't do it at this particular level because it's going to scale differently, but that's the basic idea. So the saturation of water, which is this length here, right? This length is the saturation of water. This is 30%. This is the saturation of the non-wetting fluid, which is 7%, for example. That's it. So immediately, as we look in the subsurface, what we've done so far allows us directly to be able to figure out what those saturations are. And that's really, yeah, that's basically what we're trying to do. And we've done it. So I guess we can go home. Not quite. The vadose zone seems a bit more complicated in some respects. I mean, I think this part, for the swimming pool example, seems intuitive, but this is upside down. So maybe that's strange. The vadose example is intuitive because this is the right way up. We've drawn this in the same way as before, but maybe now the swimming pool analogy seems upside down. But it's not. The analog is this. In the same way as you go below the water table, as we did here, the fluid pressure in the water is going to build linearly, like this. We don't care, because we're not going below the water table. But if you imagine this as being the pressure that it feels as it goes down, then if you imagine the opposite, and you take a column of water, and you try and hold that column of water up at this particular height here, say, then what's the pressure that you're going to have to hold to actually lift it, to just barely lift that column of water off the ground? What's the pressure you have to apply? It's going to be the exact opposite of this weight of pressure above you, which you're underneath the swimming pool. The pressure you have to apply to pull it up is going to be exactly the reciprocal of that. You know, if you go 1 meter up here, it's the same as the pressure you'd see at 1 meter down here, but negative, because it's in tension. And so you can imagine this line just being extended up through this origin. It goes through the origin here because by definition, what's the definition of the water table? Remember that from 452? It's the place, yeah, go ahead, just shout.
Where water pressure equals the force of gravity.
Atmospheric, where the water pressure is equal to atmospheric. So if we're using atmospheric pressure as 0, then this is atmospheric. Yeah, great. And so this goes through 0 here because this is atmospheric pressure, by definition the water table. And as you go up here, it just increases, but it's in tension. What about water in the swimming pool? You go from the swimming pool, Caddyshack, they've emptied the swimming pool to find the O. Henry bar. No? No. Swimming pool's full of water because who's down there? Is it Blues Brother? Who's the guy who picks up the O. Henry bar and eats it? Is it Belushi?
I think it's Belushi, yeah.
So you're in the bottom of the pool, it's air. What's the pressure in your ears? Well, it's equal to the pressure of the rim of the swimming pool plus the unit weight of air times the depth. And so the unit weight of air is 1,000th of the unit weight of water. And so as you go down here, the gradient of this green curve, which is the air, is going to be 1,000th of this. So it's almost basically the origin, the axis. If you go up for the same arguments as before, lifting a column of air is exactly the same. And so it goes up here. So now the capillary pressure, as an analog to being the difference between these two, the green and the blue, is again the difference between the green and the blue here. And so this is the capillary pressure. And so in going up here in exactly the same way as we went down, it's the same. So now if you go up, the same arguments apply. Again, you can scale the capillary pressure directly with the elevation through this expression. It's just that we're switching out the NAPL equation for the unit weight of air, which is basically 0. So it's basically the unit weight of water because of the 1,000 to 1 ratio. We can't go across here directly because it's just that the elevation is scaled with capillary pressure. But if maybe we took this capillary pressure and maybe it was up here, then we can do the same thing. This is going to be the saturation of water. And this is going to be the saturation of the non-wetting fluid. And again, it's about, no, correct me please. Wrong, right? Just gonna right? This is 100% saturated with water, so this is water saturation that goes across here. And so always, if you think about this, always the part on this lower part of the curve is going to be the water part. Always the part on the upper part of the curve is going to be the component which is the non-wetting fluid, which could be green, I guess, if I wanted to do it that way. So I think that's pretty cool. But then I'm easily amused, I suppose. And so what it's allowed us to do is it's a couple of things. It's allowed us to figure out exactly what this, we know the coordinates at this point, not in terms of capillary pressure, but we know that PC0, if that's what this is here, we can use as 0.3 is equal to J0, right? Which is equal to capillary pressure PC0 divided by interfacial tension between the fluids, permeability, and porosity. And so we know this is this because we this. So that's it. If we know interfacial tension of the fluids, a material property, if you know the permeability of your aquifer, if you know the porosity of your aquifer, the only term you don't know is the capillary pressure. And so I suppose you could figure out what the capillary pressure is. If we know what the capillary pressure is, then actually you could say something directly about scaling this curve to put a different axis on it. The axis you could put on this, instead of being a capillary pressure axis with depth, which is what it's on now, that capillary pressure is proportional to depth. And so you can basically think of scaling this capillary pressure versus saturation curve to fit the real physical dimension of your subsurface. And then you do have a one-to-one correspondence between what the saturation would look like as you went down in depth. That's the punchline of everything that we will attempt to do today. Okay, so that's probably 20% of the class if you understand up to what we've done so far. That's what we're attempting to do. Okay, important concepts, I think. So we didn't get to that last time. Let me just check what we want to talk about. Yeah, right. Gone too far. So now maybe an irrelevant example, but an interesting one. We talked before about Yucca Mountain. So these are the things we'll talk about. We did the phenomena last time, so we won't do that. This is what we've just kind of talked about. Maybe we'll do this. We talked a bit about that last time, but we'll maybe look at a better picture today. And really the question that we're trying to answer are two things. Do these things get into the subsurface? If they do, how deep do they go? And what might be their saturations? Versus depth. So those are perhaps the two questions that we might be interested in doing. So let's dial back this again. We said before that this represents the pressure in the water. And it's called the tension saturated zone is because there's enough tension here to be able to completely saturate it. In other words, the air hasn't been able to bubble into this and occupy some of the space. So that's why this curve here is vertical up to this top of the tension, so-called tension saturated zone. But as you keep on going up here, the pressures within the water get more and more tensile. And you know from fluid mechanics that there are limits to those pressures. So what's the limit to the pressure you can have within the water, the tensile pressure? Is it big, small, order of magnitude? It's related to vapor pressure in some way, right? So basically, the strength of water is 100 kPa. The reason for that is that atmospheric pressure is 100 kPa, which is what we're sitting at now, 103 kPa, kilopascals. And compared to that relatively large pressure, which is due to the column of air that sits above us, directly above us, it's the weight of that air sitting above us, then the pressure at which water cavitates is actually almost zero, and so it's very close to the 100 kPa gauge pressure that we sit at. Not absolute pressure, but gauge pressure. I guess it is absolute pressure that we sit at. It turns out that actually, even if this gets quite tensile, the ability of it to cavitate is helped by the fact that you have very small pore diameters that make it actually stronger than it would otherwise appear if you do the calculation based on the vapor pressure. And so if you look at Yucca Mountain used to be the prospective host of the nation's civilian nuclear waste, 300 meters below the ground surface. Well, you know, you've just done an assignment. This is a not very good figure, not very clear, but it makes the point of a couple of things. The ground surface at Yucca Mountain is 0. The repository was going to be at a depth of something like 300 meters. And at Yucca Mountain, the water table is and was at about 600 meters. It was the only potential repository site in the world. There must be 10 or 15 others, all of which are saturated. This is the only one that was so-called unsaturated or partially saturated. And if you look at this, this is feet, I guess, so I lied. I was correct about 300 meters, but 300 meters, of course, is 1,000 feet. So this is the repository. And 600 meters is about 2,000 feet, which is the water table. It's marked on here. If you look at measurements from the rocks that are present there, indeed, you get exactly that behavior. It's not a very good software package. It's truncated this. If you looked at the water pressure as you go up from the water table, so this would be P atmospheric. This would be, what is it? Remember this? So this would be 1, and this would be unit weight. Just by looking pressure in this axis, unit weight, elevation 1, elevation 1. This is the negative, this is going upwards. And so, just the way we've drawn this. So in other words, as you go up from the groundwater table, the pressure increases, but it becomes more and more tensile. So this is water potential in negative bars. I guess 1 bar is what we are. Atmosphere is 1 bar, which is 100 kPa, and that's here. And this is a log scale. So instead of doing it on a natural scale, if you draw this on a log scale, this would have an innate curve to it. And these are the same data. And that is this curve here. This dotted line here, which you might not be able to see because there's so much cloudy data on top of it. This curve here is dPdz is equal to minus gamma over this term here. And so you notice that actually it goes up kind of beyond the cavitation stress of this water because they're in very narrow curvature compartments where they're actually much stronger than their normal cavitation stress. So it's 10 bars, so this all of a sudden is about 1 MPa. And so this is, I don't know, I can't see what this is, but this is, if this is 10 bars, this is 20, 30, 40, this is 50 bars. So this is 50 times atmospheric pressure in tension. And those are the measured pressures. These dots are the measured pressures of water within the porous rocks as you go up at Yucca Mountain. And so it exists. It exists really intentionally. So maybe that was an aside. All right, so let's talk about answering that question that we posed ourselves before. And so the question is very simply, if you have a porous medium that perhaps looks like this, does this lens stop here, or does it keep on going down and stop here, or does it keep on going down and stop here, or does it never stop? We've drawn this as a picture. Well, we think it's going to stop. We think we know why it stops. We think we know why it stops is because the capillary diameters of these become quite small, and or because the connection between the surface and the subsurface becomes broken. I'll explain that later. In other words, if this tail is cut off. And actually this tail is essentially cut off. We've said that this little stippled region here is really just the smear that goes down as this water flows, and it's left a small smear on the grain coverings that are left there, which nonetheless is a problem because it will dissolve as the water goes downstream, and you'll get a plume coming out of it, which is this stuff here. But it's really a smear, and it's not connected. But we think there's something to do with the small pore diameters that we have here that stops water from going into it. And so let's see what we can say about the physics of that. And so one question is, when will it stop, and what are the mechanisms by which it stops? We think that one might be due to the fact that we have a capillary barrier. But one thought exercise that we could do, which I think is interesting, is to take the salad dressing off the table and to look at that in a bottle. It's water, I guess vinegar probably is mainly water, with oil sitting on top of it, which floats on the vinegar. And so if we have the denser fluid on the bottom, water, and we have the lighter fluid on the top, which is gasoline, wouldn't want to drink it, or olive oil, then we're accustomed to seeing them segregate themselves. If we took a denser fluid rather, and we inverted it so that the dense fluid was sitting on the top and the lighter fluid was sitting on the bottom, can that be? Is it possible? What do you think? Probably not very easy. It's probably like balancing there's an analog in this to taking an upturned one of those stainless steel food bowls and balancing a ball bearing on it. It's not very easy to keep it on the top because it tends to roll off. It's quite easy if you flip it upside down and put the ball bearing inside it because it exists within a well. And you can think of those as graphs of maxima versus minima, valleys versus crests, and what those mean in terms of stability of systems, mechanics. We don't need to go into that. But the answer could be that there's no physical reason that if you're very careful that you couldn't take water and put a denser immiscible fluid on top of it, maybe if you had to put it on with a straw. I think, I wouldn't know this of course, but I think you can actually get drinks, mixed drinks in bars, where you introduce layers of different fluids which might have different densities in them, and so you have this stratified drink. What's a B52? Is B52 that? Yeah, it's a long time. I can think of another name with a very different name, which I won't mention in this class, because I'd like to keep my job probably for a little while longer. But yeah, but there's no reason why you can't do it. And the reason why you can't do it is there's no intrinsic reason that if you had overlying this a dense material which could hold itself together, that it couldn't do that. The problem in doing that is that if you take this denser material on top and you just put a little nick in it so that now there's a little perturbation in it that happens to develop this. is that this perturbation, if you do the calculations to calculate exactly what the pressure is on this side of the perturbation and on the top side of the perturbation, what you'd do is you'd find out that the pressure on the top is larger than the pressure underneath. If the pressure on the top is larger than the pressure underneath, it'll move downwards. If it then gets a bigger pressure on the top, then it'll keep on going. And that's why you get this inverse lava lamp. So this is an attempt to explain that. You can calculate the pressure so this is in a swimming pool still. You can calculate the pressure on the top just by looking at the height of this down to that point. The pressure is going to be the unit weight of the fluid on top, the red fluid, times its height. It's equal to H, which is this amount, plus a little bit which we've added onto the bottom, which is delta H. If you look at the pressure on this bottom part, then the easiest way to get that, you remember that if you can get simply connected in a fluid to this point, the fluid pressure here is going to be exactly the same as the fluid pressure on the horizontal level. dP dx is equal to 0, you might remember. It was one of our fluid static issues. So the pressure at this point here is going to be this amount of this fluid plus delta H times the other fluid underneath it. This amount of the red fluid, this amount of the blue fluid. If you add these together, this density unit weight is always less than this, and so the red term has to be less than the blue term, always. If delta H grows, then red is even bigger than blue. And so that's really just a physical explanation of what happens. It's an instability that develops not because of any physical reason that you can't have these two on top of each other, but if there's a small crenulation on the base of the interface, it can't be sustained because the instability grows. And it'll grow by this becoming a bubble that just sinks to the bottom like a lava lamp, a cold lava lamp. So that's in a swimming pool. So now we're going to take it in a porous medium. I really like red for some reason. And so now what's different when we talk about a porous medium? What's different about a porous medium is this capillary pressure versus saturation curve, which we spent a lot of time talking about. And in particular this point here. And that is that if the pressures here are the same, then nothing happens. If the pressures here are different, then everything happens. It only has to be a tiny difference. Here, the pressure difference that we have to get between the two fluids has to be more than just an infinitesimal amount here. It has to be a finite magnitude. And that finite magnitude has to be PC0 before anything happens, because you've got the porous medium resisting it. In the swimming pool you don't have that, but in the porous medium you do. And so if we go into the porous medium, then we can think of the same kind of example. We take our 55-gallon drum, we put that on the surface. It has some height to it, h sub c. And the question is, does that go into the ground? We know the pressure here for the red fluid is going to be this. Right? Ignore that this is 0 for now. This would be the pressure that's on the ground surface. We know the pressure here in the blue fluid has to be atmospheric. And in our parlance, that is 0. PC is equal to P non-wetting minus pressure of water. We have water underneath here, which is at 0 pressure. We have the non-wetting pressure, which is bigger than that, which is this. And therefore, if this height here happens to be, so this is 0. So if this non-wetting fluid pressure happens to be PC0, and that is a physical material property, this, then it will invade the system. And so immediately we can say that we know exactly what kind of pressure we have to apply to be able to get it in there. It's equal to this material property. So if you like PC0, don't forget that this is a material property. And if you want to just draw the capillary pressure, saturation versus capillary pressure curve, it is exactly this point here. This is PC0. This is 0 to 1. And so this is a material property. This is a material property. And so if you know those two material properties, presumably you can calculate how high you have to have this column in the drum before it goes into the ground. So that may be useful. I'm thinking that's useful. I think that's really useful. So based on that, it can develop this little pathway that will take this most open pathway, go into the ground. It'll go to here, maybe it'll go to here, maybe it'll go to here, maybe it'll keep on going forever. And so I guess the question is, what causes it to stop? We think we know something about capillary barriers, that it might want to then only go this deep and then pond on top of this. If we have, say, the diameter of this is very small, that's kind of our definition of capillary barrier. But I suppose one other question we could ask is it even going to get there? Why doesn't it stop here? Can it stop here? What would be the conditions that would make that happen? And so to answer that, what we could do is we could take the same analysis that we had before with this kind of analysis. What we did was we wrote the equations for behavior at this particular point here, and we just did a force balance. If this pressure ends up being bigger than this pressure, then it can move. If it moves, it keeps on going. The only time it will stop is if they're equal to each other. The difference we have now is that we have this kind of activation barrier to overcome, that we have to get the difference between these pressures basically has to be larger than this difference. So in other words, if this pressure isn't in excess of this pressure by at least this amount, then it won't move. We're adding another resistance onto it. So initially it's just the water pressure at that depth, but there's an extra resistance because it has to get into the pore space. So if we take the pressure in the water plus this PC value, and if this value isn't larger than it, then it will stop, or it won't get going. And so that's basically the idea. We do the same calculation at this interface. We recognize the fact that if this is connected, so in other words, if you can get from this point here to this point here, and only go through red fluid that fully saturates the pore space, then it's just the same as being in a swimming pool filled with this NAPL, that you're feeling this pressure in your ears at the bottom. And then perhaps not living for so many years after that. And likewise, in the water, if you can go from this point here to this point here in the water, then the pressure is just going to be equal to the height of water. Exactly the same as before. And so it's this simple connectedness of the systems that we're talking about. And so that's basically this expression here. If the pressure in the non-wetting fluid, the red, wants to move down, then it has to be at least as big as the resisting pressure, which is probably going to be larger than, plus the extra resistance to the invasion pressure, getting into the pore space. And we can calculate what each of these pressures are in the non-wetting, just the height times the unit weight of that fluid. The height is h. The pressure in the water is just going to be the height, the depth in the water, multiplied by the unit weight of water. And the resistance in the non-wetting fluid is going to be PC0. And because these are written as pressures, as a multiplier of, we can just use PC0 as a number. If you wanted to write it as a function of a head and a non-wetting fluid pressure, unit weight, then we could write it this way. But this is just PC0. And so if we solve this to be able to figure out exactly what the minimum height of fluid is, what this height of fluid would be for this to happen, then we find out that we get this minimum, make this circled value of H minimum, and we end up with this item here. This is a material property. Let me draw a square around it. This is a material property of the porous medium. This is a material property of the non-wetting fluid. And this is a material property of the water. And so you see material property, material property, material property, and it defines a parameter. And physically, what I think it says is that this length here has to be at least equal to h min before it will go, before it will keep on moving. If the height h, so if h is greater than h min, then it goes, for want of a better word. Goes down. Stupid annotation, but makes the point. So that means if it goes at h min, then as it gets longer, for instance, then it'll still keep on going. So there's nothing really stopping it from keeping on going. But what you could imagine, let's back up one step. When we looked at this, we came up with a different value, right? We said basically that this will go as soon as it gets to h sub c. H sub c is this material property, and so as soon as we get to this particular height, then it's going to seep into the ground. In this geometry, we've said something that maybe contradicts that. We've said it only goes when it equals this amount divided by some number which is less than 1, which means that h min would actually be larger than this. So this length here, for it to go, is larger than this length here. So the question is, why is it different in the first place? And does it make sense that it's larger? Because clearly to get into the subsurface here, we're going to have to overcome this behavior, this resistance. And clearly to go further here, we have to overcome this resistance as well. So there's a subtle difference between those. What is it? Yeah, go ahead, Carl.
In the first case, the water isn't occupying the space of the HC.
Right, up here. So why does that make a difference? Is there a...
You're not overcoming the fluid pressure of the water as well.
Yeah, so it's buoyancy, right? It's basically buoyancy. So you don't have to overcome the buoyancy of this. So this, if you imagine it sitting in water up to this, really the effective pressure of this is its buoyant weight. It's its weight minus the weight of water that's all around it. And so, yeah, so that's exactly the same thing. So in other words, you're having to overcome this extra amount in this particular case. And so as a result of that, we can say two things. One is that this length has to be longer for it to start moving. And the other thing is that even if it detaches from here, if you've emptied out this barrel and it now clicks off at the top, pinches off, and moves down as a ganglion, so long as it's as large as h min, it'll just keep on going. It'll happen to happily shift down through here. It'll keep on going. The only thing that will make it stop is if this breaks. And the reason, and if this breaks, and now that the new lengths are less than this minimum value. And the rationale for that is that this length here is atmospheric, and it's really the pressure change that's occurring over this connected path. If it's broken, it's no longer connected, and so if individually these are less than this minimum value, then all of a sudden it'll stop. And so there are two values. And so, that's probably, yeah. So the practical implications you can see are exactly the ones that we've kind of suggested. To get it into the ground, it takes less than you'd need to keep it to sustain it, which is interesting to know. We can calculate what that height would be for it to do that. This is really h, not h sub c, but it's synonymous with h sub c. Once it's in the ground, it's existing at its buoyant pressure because it's got water all around it, and therefore the change in height you need for it to be able to build up that large pressure at the tip to keep it going would be larger in the first place, and it has to overcome the resistance to, well, in the previous case I guess it did as well, and it now also has to overcome this resistance to get into the pore space, and so we can calculate those. And the consequence of that is that as it travels down at some stage and breaks off, then it breaks off into two parts, then it would be immobile. And so you see some shades of that, I think, in these, right? In these figures. This has stopped prematurely. It's run out of material to go down, and it's run out of impetus to move down. This one has kept on going until it's reached a really significant capillary barrier, which is at a low permeability and large entry pressures that it can't overcome. And in this case, I presume that the reason it stopped here is that this is just maybe this isn't a continuous phase where it's completely oil. And so in other words, the pressure that this free phase would be seeing is only the very thin pancake of this that it has here, and not all the supernatant flow that goes up to the surface, because no longer is it continuously connected. So those are important points. In this case, this is continuously connected just by the density of the red lines that you can see here. So the pressure that you'd have exacted here would be the full weight of here, albeit submerged in water. And this has drained everything into this. The other picture of this, maybe it's probably worthwhile looking at this as well. So it's epitomized here. We've said that. Yeah. The other picture of this is, if I can find it, coming back to this, which might make more, hopefully might make more sense now. Unfortunately, I was trying to look out to see if it has page numbers on this. It doesn't have page numbers, that I could go back to a page. But if you remember this figure, yeah, fantastic. Yes. Ooh, it does. So remember we talked about these different kinds of saturations. And I can't draw it very easily underneath it, but I could draw it here. Is that this capillary pressure versus saturation curve, water from 0 to 1, capillary pressure. Let's just look at the well, what would we be doing? Let me use two different colors for this. So remember we talked about these particular curves, and so we said that if you start with an oil reservoir, these are the grains and stipples. The black is oil, the white are water. Grain to grain, the white covers the surfaces of the grains, maybe at a monolayer, but at the grain to grain context, there's a little donut that sits in it, a torus that sits in here, which will have a wedge-like shape, which is this here that goes around the grains. It's almost 100% oil saturated, so we're up here somewhere, right? So this would be the non-wetting. This would be oil. So this is 100% to 0. This is water. So as we come down here and we push more and more water in, we come down here. And so the point is, you can imagine at this case, if you stuck a straw in here and sucked, what do you think you'd get out of it? Black or white? You get oil. Oil is absolutely connected. do you think you would get any water out of it? Why?
The little waters in there is on the monolayer of particles.
Yeah, but there's also this little wedge here. But there's also this torus. But because they're grain on grains, they're donuts. The donuts aren't connected to other donuts, so they're not connected. And so the connectivity of it is kind of important. I think it's right that you wouldn't get any water out of it. So you suck oil out. You have to replace it with something. You pump water in. The water gets larger. At some stage, the donuts of water, instead of being isolated from each other, all of a sudden are connecting within the pores. You suck out of here, you get oil and water. Keep on sucking both. You deplete the oil. All of a sudden, you suck out of here. You can't get oil, but you can only get water because it's funicular saturation. Definition of funicular was the cog railway. If you want to get the oil out of it, you have to travel with a water railroad that carries the oil out in the water railroad car, basically. So in other words, as we come down here, this would be 1, this would be 2, and this would be 3, this would be 1, this would be 2, and this would be 3. And so it's important to be able to think about this in terms of the connectedness. And so what we were talking about before was defining the capillary pressures in terms of the column heights. And in this particular case, we made the case that if you're in a swimming pool and you fill the swimming pool up with sand, you put NAPL in it and water in it, so long as you're connected all the way from the surface down to the points in those different fluids, you'll see the pressure in those fluids, which is equal to unit weight times depth of that particular density. But if it's not connected between the surface and that point, or 2 points, then you can't use that calculation. And so I guess in this case, the NAPL would be connected, the water would not be connected. So you wouldn't necessarily have a way of calculating the pressure within the water just from this unit height. In this case, they'd both be connected, and you absolutely could. And in this case, the oil wouldn't be connected, so you couldn't necessarily do the calculation. In fact, in this case, you might think that the oil bubbles surrounded in water at some given pressure would have the same pressure in the bubbles as in the water. But there is some interfacial tension there, but not in contact with the rocks. So it could be different, but it would be largely the same. And so that's the relationship, I guess, back to this. All right, and so that's almost the last thing. Okay, so yeah, we made the point about why these are different. And so they represent different physical situations from each other. This is cut off, but the reason was the one that we explained. And so finally, if we want to measure these capillary pressure curves, well, we've already gone through it, but we didn't look at the piece of equipment, and that's probably useful. And so let's spend a couple of minutes just clearing this up. I explained it slightly differently. I explained it wrong actually last time. I'll take that video down and discard it. There's a better one from last year. And it was wrong in that I defined it as the case where, you can probably tell me why it's wrong. I tried to salvage it by drawing the capillary pressure versus saturation curve backwards. Really wasn't quite true. And this is our curve. You remember what our curve looks like. Kind of comes up from here and goes across here, right? So what does that mean in terms of this experiment? So what this means is in these measurements, typically water-wet sands, sandstone sands, mean that it just loves water. It wants to cover the grains with the water, and so it's water-philic, not phobic. It's hydrophilic. It sucks it in, and it spontaneously imbibes the water. So it's most happy if it has water here. It's not so happy if it has oil. So the natural condition for it to start in, even though you might start with a reservoir with petroleum in it, the natural condition is to think about it starting with water in it. So this is a core that's water filled. It sits on a frit, which allows water to go out of it, and you surround it with oil, which is this stippled material. Initially, the pressure in the water and the oil are the same, and so by definition the capillary pressure is 0. You increase the pressure in the oil, doesn't have enough oomph to invade. At some point, all of a sudden it invades, and you get a slither of oil going into the sample, and that slither of oil going into the sample pushes out water out of the bottom. Because of mass balance, there has to be a height rise in this tube. If the tube is very thin, but doesn't have much capillary resistance, a small amount of water gives you a relatively big rise in the tube, so you can measure it. You keep on increasing the pressure. Another slither fills up the next largest pores within the system. Again, it displaces a slug. This rises a bit more. You end up with a new pressure that you go up to here. So you add a new pressure up to this point, and slowly, over a bit of time, it equilibrates. You measure the amount of volume change in here. You can calculate the change in saturation, because you know lots of other things. Again, you increase the pressure. Again, you get an equilibrium point. So you end up being able to put this curve together from this. The curve will look something like this. And you go up and it'll asymptote to infinity. You stop it, and now you do the reverse. You backstep. You start off with the pressure up here. You drop the pressure to this point. It slowly equilibrates. You get a new point. And so physically what's happening is it's sucking this stuff back in. It sucks it back in because it imbibes. And so the rationale for us calling the curves the way we did, that this curve going up here is drainage, is because the water is draining out of it. Oops, I did that wrong, didn't I? You should have told me, yes.
What's stopping that oil from just penetrating the frit directly? Why do you have to go through the pore? Like, what's stopping it?
Because the frit is engineered so that the grain size is big enough so it will not allow the oil to go through, but will allow the water to go through. So the grain size is intermediate to it. That's good question. And so the imbibition curve is because it imbibes the water. If you put the water back here, it's happy to suck it back in. It only has water in here. It's only displaced water because all the other oil that's been pushed into this has been kept inside this core. Isn't it that? So it'll suck the water back in, and then you get the imbibition curve as it comes down. So that's the kind of mechanism of the test. And so it's kind of explained the other day, but incorrectly. Some details were incorrect, but that's basically the experiment that's done. And that allows you to get a capillary pressure versus saturation curve. And if you have that curve, you can do all the things that we talked about today in terms of figuring out exactly how saturations will change in the vadose zone as you go above the water table, where the two fluids are air and water, and below the vadose zone where you have a NAPL going in it, where the two fluids are water and NAPL. Always we'll assume that the water is the wetting fluid that likes the quartz. Not always true. Limestones, that's not the case. Limestone sands, for instance, is not the case. And always the non-wetting fluid will be either air or the NAPL. And so that kind of allows us to be able to say something about this behavior in terms of what this would physically look like. And we've said that this occurs in days, weeks, months to get to this architecture. So if we want to know something about how quickly it progresses to that, and to follow the saturation profile, and also to follow how quickly we can suck it out of the ground, and what the constraints are on that, we need to know something about the next step. And the next step is that we need to be able to use Darcy's law, which tells us something about the rates at which fluids flow in the subsurface. But instead of writing Darcy's law as a pressure gradient and a hydraulic conductivity term that gives us a flow rate, no longer do we just have one fluid that we have to worry about, but we potentially have to worry about two fluids. We have a NAPL that's in place, and we have a water that's in place. And so the next step is to be able to figure out exactly how we solve problems for flow when we deal with two fluids instead of one, so-called multiphase flow. And so that's what we'll talk about next.